Okay, let's dive straight into this explainer. Today, we're taking something that feels like instant magic, loading a web page, and tearing it down to the raw engineering pipeline underneath. We're going to trace the exact journey from the split second you smack the enter key across global networks all the way down to painting literal, microscopic pixels on your screen. Because, look, we type URLs all day long, right? But stop and think about what is actually happening under the hood in those passing milliseconds. To most people, it's just internet magic. But to us engineers, it's a brutally strict sequence of steps, managing state, battling latency, and locking down security. I absolutely love this quote because it hits the nail on the head. There is no magic here. The browser isn't just slapping HTML onto a canvas. It's running a highly complex, multi-stage rendering pipeline. And honestly, deeply understanding this pipeline, that is the exact difference between building an app that feels lightning fast and one that's a janky, frustrating mess. So here's our roadmap. We're heading 5 key stops today: the network journey, securing the connection, building the object models, the rendering pipeline, and finally, performance and optimization. Let's get into it. Section 1, the network journey. Finding our destination. The absolute first thing that has to happen is translating a human-friendly domain, like google.com, into a machine-routable IP address. DNS is basically the internet's address book, but to avoid crazy global latency, it relies heavily on caching. Your browser checks its own internal cache first. If it strikes out there, it asks your operating system. Still nothing, then it asks a recursive resolver, usually from your ISP. And if that fails, it does the real heavy lifting, climbing up from root servers to TLDs, and finally to the authoritative name servers just to get that one exact IP address. Section 2, securing the connection. Because even though we have the IP address, we can't just start blasting data. We have to build a secure tunnel first. And right here is where latency really starts to creep in. HTTP relies on TCP to guarantee that data arrives in order and uncorrupted. But to set that up, TCP demands a 3-way handshake: a SYN, a SYNAC, and an ACK. This intrinsically consumes 1.5 round-trip times before you've even asked for a single byte of the web page. So if your ping is 100 milliseconds, you've just burned 150 milliseconds literally just saying hello. Right on the heels of that TCP connection, the TLS handshake kicks in. Since standard HTTP is just plain text, we absolutely need TLS for encryption. This handshake uses somewhat slow, asymmetric encryption, public and private keys, to verify the server's certificate. But once verified, the client and server negotiate a super fast, symmetric session key. From that moment on, the whole conversation is securely locked down using that incredibly fast key. Okay, so your secure request finally navigates all the global routers, CDNs, and firewalls and hits the backend stack. An event-driven server like Nginx catches it, hands it off to an application gateway like PHP-FPM to actually do the thinking, maybe run some logic, query a MySQL database, and then stitches together the final HTML string. Nginx encrypts that HTML and streams it right back down our secure tunnel to your browser. Section 3, building the object models. This is where we finally start structuring the data. The browser receives those raw HTML bytes, and the heavy lifting begins. It converts those bytes into characters, then tokens, and instantly into nodes, parsing top to bottom to build out the document object model, or DOM. Think of this as the structural skeleton of your web page. And remember, the DOM is a live, breathing API that JavaScript can talk to. It is way more than just static HTML source code. Simultaneously, whenever the browser hits a style tag, it starts building the CSS object model, the CSSOM. This is basically the clothing for our skeleton. And here's a crucial takeaway. The CSSOM is entirely render blocking. The browser will absolutely refuse to paint a single thing on your screen until all CSS is parsed. Why? Because rendering with partial CSS gives you that awful, jarring flash of unstyled content. It has to figure out the cascade, specificity, and inheritance first. So how does this come together? The browser merges the DOM and the CSSOM to create the render tree. Now, this tree only contains the visible elements and their final computed styles. This is our fully dressed skeleton, ready to step out the door. And this brings up a massive gotcha that catches developers off guard all the time. If you have an element with the CSS rule display none, it exists in the DOM skeleton, sure, but it is completely stripped out of the render tree. It takes up 0 physical space. But on the flip side, if you use visibility hidden, it actually stays in the render tree. It still takes up layout space as an empty, invisible box. Section 4. the rendering pipeline. It's time to actually draw some pixels. Welcome to the critical rendering path. This is the exact sequential workload the browser runs to turn code into screen pixels. We parsed our trees, so now we move into layout, paint, and composite. During the layout phase, which you'll sometimes hear called reflow, the browser traverses that render tree top-down. It's calculating absolute screen pixels from relative things like percentages and auto margins. And let me tell you, this is an incredibly expensive process. Layout is recursive. If you change the size of just one single element, it can trigger a total domino effect, forcing siblings to shift and parents to resize, prompting a massive recalculation. Next up is the paint stage. This takes those carefully calculated boxes and generates exact drawing instructions, like filling a rectangle, drawing text, or rendering a shadow. But it doesn't just paint everything onto one giant flat canvas. It actually organizes elements into separate layers. Then, the compositing stage takes over and sends these painted layers straight to the GPU, flattening them together into the final image you see on your monitor. Section 5. Performance and Optimization. Engineering for absolute speed. All right, this is where it all comes together. Not all CSS changes cost the same. If you use JavaScript to change a layout property, like width or margin, you force the browser to rerun layout, paint, and composite. That is a wildly high cost. Changing a color, that skips layout and just triggers paint and composite. But if you animate composite-only properties like transform or opacity, you skip layout and paint entirely. The browser offloads it to the GPU, giving you that buttery smooth 60 frames per second. You know, we can also give the browser a massive cheat code using modern CSS containment. Take the property Content Visibility Auto. It basically tells the browser to completely skip the style, layout, and paint work for anything that's currently off-screen or below the fold. For a really long, complex page, that is an absolute game changer. So, to wrap up the best practices from mastering this critical path, inline your critical, above-the-fold CSS to dodge those render-blocking network requests. Keep your DOM tree shallow so parsing and layout fly by. Strictly animate on the compositor using transform and opacity. And please, when using JavaScript, batch your DOM notations. Never interleave reading layout properties with writing them, or you're going to cause brutal layout thrashing. So, we've taken what looks like web magic and broken it down into pure, sequential engineering. We've seen exactly how DNS lookups, TCP handshakes, object models, and the browser's rendering pipeline totally dictate your user's experience. Which leaves us with one vital thought to walk away with today. Knowing that the absolute fastest render is the one you never trigger, how are you going to engineer the hidden journey of your next web request?